Thank you. I'm going to talk about creating procedural macros in Rust. These are lessons I learned when I created a Rust macro for myself, maybe of interest to other people, called anyinput. And we'll use that macro as an example. We'll talk about it more, but it's basically to make it easier to write functions that can be permissive in what kind of inputs they allow. So by way of introduction, 11 years ago, I was working as a developer at Microsoft Research in the Seattle area, and we created a genomics package called FastLim that we open sourced. That was written in mostly Python with some of the performance pieces written in C++. 3 years ago, I retired and began work as an open source volunteer, continuing to maintain the FastLim project. Most of that work involved things like updating the Python from version 2 to version 3 and just kind of keeping up with some user feature requests. 2 years ago, I finally just became fed up with maintaining the C++ part of the code and replaced it with Rust. And that was successful for the project. And it also led to an article called 9 Rules for Writing Python Extensions in Rust. Last summer, I pulled out a piece of the genomics package that reads a particular genomics format called BED and made that available. It was already written in Rust, but it wasn't easy to use from Rust. It was made to be easy to use from Python. And I wanted to see if I could make an API in Rust that was as good as what I was able to make available in Python. I think I was. It was more work to do it in Rust, but I think for users, it's just as usable as Python. And that became an article called 9 Rules for Elegant Rust Library APIs. Finally, this fall, I simplified the Rust code with this new anyinput macro. And along with this talk, you can get all the details from an article on medium.com, specifically towards data science, called 9 Rules for Creating Procedural Macros in Rust. So let's talk about the anyinput macro that I wanted to create. And I'll start with a question that everybody can kind of ask themselves. If you were writing Rust and I ask you to write a function that accepted any kind of string-like thing, would you know how to do that? In other words, instead of just taking a stir or a string, you could do it borrowed or moved. There's also references to strings that can be borrowed. Could you make a function that could take any kind of string? So your user wouldn't have to match your kind of string. I bet I can kind of remember how to do that. So that's not the hardest thing in the world to do in Rust. But what if I asked you to do the next thing, which was to write a function that it could accept as input any iterator-like thing, where each component of the iterator was any path-like thing? It's getting more complicated. I'm sure some people can do it. I'd have to look this up every time I would do it. And then the final challenge here is, what if you're using the multidimensional array package, NDArray, but you want to accept a normal Rust vector of F32s? Would you know how to have a function that could take a vector of F32s, but inside your function, it would look like an ND one-dimensional array view? And I didn't even know that was possible for most of the time. The point of this macro is to make that easy. And we can look at an example on the left. Starting at line 3, we can define a function that uses this macro. We say pound anyinput. We define a function called length +2. It has an input called s, which is of type. It's not a real type. It's our special type called anyString, and it returns a usize. And then inside our function, we just say s dot length +2. That's what our function does. And you may not believe that this can take any kind of string, but you can see starting lines 10 through 18, I'm passing in strings, strs, references to strings, and sometimes they're borrowed and sometimes they're moved. So that demonstrates what the macro can do for strings. And on the right side, we've got a more complicated example. Now we'll say we want to define a function called toIterSum. Its first input is called iter1. Iter1 is any kind of iterator of u size. And iterator2 is any iterator of any string-like thing. And the function returns a u size. And then inside the function, we're going to sum up the numbers we get in the first iterator. And in the second iterator, we'll take the length of all the string-like things and we'll add that to the to our accumulating sum, and then we'll output it. And at line 13 on the right, you can see an example. We call toIteratorSum on an interesting iterator, an iterator where we're iterating from 1 to 10 inclusive, and then also an array of strings or strs or something like that. And that works fine. And we can call the function, it'll return the correct answer, which in this case is 61. So that's what the macro I wanted to create and have created does. So how do we create a macro like that? The simplest kind of Rust macro is called a declarative macro. With that, you use the macro rules macro to create your macro. When you can use it, this is the right thing to use. It's simple to use, easy to read, but not as powerful as I needed for this project. The other kind of macro are procedural macros. There's 3 specific kinds, but they're all very similar with respect to how you program them. So there's function-like macros, derived macros, and attribute macros. The attribute macro is the one we'll be using. That's where, like on the top of a function, you can say pound square bracket and the name of your macro, and that'll cause your macro to be called. On all these procedural macros, what happens is you write your code one way, and before the compiler actually compiles your code, it sends a token string of the code that you wrote into a function. That's the main thing you're going to have to write. Your function is going to return a token string, whatever that is. We'll see that in a bit. That you can think of it as your original thing expanded or modified, transformed some way. And then that second thing, after it's run through your macro function, will be what the compiler actually compiles. So I could have called this talk 9 suggestions for making procedural macros, but if you call something just suggestions, it's kind of boring. So I'm going to call them rules, but that doesn't mean that I'm really the authority on this and that you have to do everything I say. There really are suggestions, but I think it's just less wishy-washy for me to be a little bolder and call them rules. So we're going to look at the rest of the talk will be 1 slide per rule for the 9 rules. 4 of the rules will relate to syntax trees, how to convert among the various types related to syntax, how to learn about the syntax tree data structures that you'll need to work with, how to construct new syntax trees for your output, and when you need to recursively manipulate syntax trees, how to do that in a way that's not too terrible. There'll also be 5 rules related to other topics, including how to develop your project your macro project as a non-macro project. It sounds a little strange, but it turns out that makes things much, much easier. How to create unit tests that you can actually debug, how to do error handling, how to do integration tests, including UI tests, and the importance of following the rules of just general elegant Rust API design. So turning to our first rule, the first rule is that you should develop a procedural macro as a normal non-macro project. That means your project will actually have 3 projects. There'll be a top-level project. It'll be very small. Most of it will just be your documentation. The only important part of it is to re-export a function that's defined in the next level project. So in this case, the next level project, which I'm calling the derive project, defines something called anyinput_derive anyinput, and that in the top level project doing that pub use anyinput derive anyinput means that our top level users will see that anyinput function at the top level. There's not much more to the top level than that. So that brings us to our second level project where we actually define the macro. That will be a function that, in this case, anyinput, that takes some token stream input, or in this case, inputs, and returns a token stream. In my code for this level, and I recommend this, I only have 11 lines of code, because what's really going on is I define this function anyinput, and all it does is call anyinput_core, passes the 2 inputs to it, and then takes the output from anyinput core and returns it. And you'll notice some intos. That's because there's actually 2 kinds of token streams that are designed to be very similar and interconvertible, and doing those .intos tells the compiler that it can convert them for us. So we've had 2 levels that have done almost nothing. The core project is where the real work gets done. We define a function. In this case, I called it anyinput_core. It takes some inputs of type token string and returns a token string. Now we'll actually write a bunch of code that'll do the conversion of the code that we want. So the user will give us, in the anyinput case, a function, and we'll see this in a bit, and then we'll return the modified function. And we can have lots of other code for helper functions and all kinds of data structures and unit testing. So you may think it's confusing to have 3 Rust projects when you really only wanted to write 1. Anytime you do macros, you're always going to have 2. The top 2 I have here. I strongly recommend adding the third, because it makes debugging much easier. It allows you, because the core project, the bottom one, is a non-macro project, you can do things like set breakpoints. I use VS Code. So you can set a point in your code, and VS Code, a breakpoint runs line by line, single line at a time, look at your variables, just all the normal stuff you would do with coding becomes available at this lower level core project. It's not available at the derive project, and that's why we keep the derive project so small. One help with having to have a thing that you think of as 1 project be 3 projects is Rust has a feature called workspaces, where you can tell it that these 3 projects are coordinated and work together. And if you read the article, it'll talk about how to set it up, these 3, as a single Rust workspace. And so that means the overhead of having 3 projects isn't too bad. So rule 2 is we want to create a procedural macro, you need to be able to freely convert between token streams, syntax trees, strings, and literal code. And we haven't defined token streams, and we don't know what syntax trees are, and I guess we know what strings are. Let me give an example. So look at line 5, that this is a first implementation of the anyinput function at our core level. It has the first input args of type token string. We're not going to use that input. The second input is called input. It's of type token stream. That'll be a tokenized version of the user's, in this case, function. And we're going to take that, and at line 6, we're going to call the parse2 function and tell it that we'd like it to convert the token stream called input into a syntax tree object called item fn, item function. And that'll be called old item, be assigned to a variable, old item function. Then we're going to put that old item function into a function called transform function, which you can see at line 11. Transform function will take an item function, do some things, and then return an item function. Specifically, the first thing it will do is print whatever the item function is. And we can do that with print line and this quote macro with that pound sign. It's kind of a little magic syntax. But if we do that, which we do as a debugging, like during development while we're developing, if the user passed in a function called hello universe, print hello universe, you can see it down below in the white, it would print the string hello universe, function hello universe, print hello universe. We can also see this item function thing as what it is, and it's a piece of the syntax tree. All the syntax tree is a nested structure of structs and enums that are defined in a crate called syn, S-Y-N. So if we told it to print the syntax tree, it would start by printing what you see in the lower line of the white, item function, and you can see that's a struct, and the struct has an attribute called attrs, which is an empty list or array, and it has a field called viz, which has some value inherited. We'll see how we can learn what these are. It has something called signature, and so on. So looking back at let's look at line 14 in the function. We've printed out the user's function in syntax tree form to strings. We're going to return a bit of code, and the code we're going to return, no matter what, in this first version, no matter what the user passed to us, we're going to return the function hello world that does a print line hello world. And the way we do that is, you can see lines 15, 16, and 17 are that function. And by putting them in the parse quote, which you can see at line 14, that's a way that to capture literal code, which is lines 15, 16, and 17, and turning it into an item function. And it knows which item function because it knows the return type of transform function. Anyway, think of it this way. There's these 4 kinds of things: token streams, strings, syntax trees, and literal code. And we might want to convert between any of them. There's functions to convert every which way you'd want. They're a little bit hard to figure out, a little bit hard to remember, but you're in luck because I made a table. So here's my, on the right, you can see my table of 16 combinations of things that you might want to convert to and from, and what the exact Rust syntax is to do them. So this is in the article. I'd recommend keeping this at hand. I was using it all the time. So from rule 2, we now hopefully have some ability to convert among all the types that we have to deal with. We want to start, we'll say we're going to start in kind of a test-driven manner. So we want to create debuggable unit tests. And let's look at an example of what one of those would look like. This is just in our lowest level core project. We define a test, just like a normal Rust test. This one's called one input. And the first thing we do in line 65 through 68 is we show what a user's input might look like before we apply our macro. So the user might have something called any string length that takes as input S of the pseudo type any string and returns a usize. So we call that before. We also, starting in line 71, show it what we want what we expect the function to be converted, what do we expect our macro to convert this function into. So you can see it's still a function called any stir line, but now it's got a generic type called any string 0. And that's now the type of our input, the actual type. And there's a where clause that says that any string 0 is specifically an asref stir. And also line 76, you can see that we expect that the macro will add a new line. It'll say s equals s dot asref. And then after that, the rest of the code should stay the same as it was before. So we have our before code, our expected code. At line 81, we just pass in our before code to our main core function. Mine's called anyinput core, and get the after code. That'll return token strings. And then we can just assert that the token strings we expected, the ones are expected, are the same as the ones that we actually got in after. And any tokens EQ is a little function I created. You can get it from GitHub or from the article. All it does is make sure that the two things are equal. And if they're not equal, it does a line diff to help you figure out where something went wrong. And then finally, on these unit tests, I usually take another copy of the after code and just run it on something. So here I'm taking any string length and applying it to the string ABC and verifying that it equals 3. And that's just to make sure that this thing is doing about what we want. The nice thing about putting this in the core, the lowest level project, is again, we can set breakpoints. So if something isn't working, we can set a breakpoint at line 82 and then, line 81, where we call any input 1, any input core, and we can actually watch the code. We can go into the code and watch it execute line by line, look at variables, and that makes debugging much, much easier. So one of the hardest things about writing procedural macros is that there is this huge number of enums and structs that are used in the syntax tree format. And it's not immediately obvious how to learn how to use them. So here's my recommendation. Take a function that you're curious about, for example, what's in the black rectangle at the top, and then go to AST Explorer, which is a website, Abstract Syntax Tree Explorer. Make sure you set it to Rust. When I first went there, I only saw the JavaScript version, and I got very confused. But there is a Rust option there. You can paste your little function into AST Explorer, and it will output what's in the gray box on the left. In this case, we can see that it sees a file and some things, and then an item fn. We think, oh, maybe the Rust syntax tree representation for a function is an item fn. What's an item fn? Well, it looks like it's a struct with 3 fields, attrs, viz, sig, and block. Sig itself is of type signature. Signature is some kind of struct with a bunch of inputs. So that gives you just some clue that you're, in my case, that I'm interested in the syntax tree struct types of like item fn and signature. When you know those, you can go to the documentation for the syn crate and just look them up. And you can go and say, oh yes, item FN does represent functions and it does have these 4 fields. And now you've got kind of a hook to let you get in and understand what you need to understand on the code that you actually have. This also gives you an opportunity to use kind of the normal Rust destructure and pattern matching to access parts of the struct or the enum, parts of your syntax tree. For example, in my code, there's a situation where the function that the user gave me may or may not already have a where clause. If it does have a where clause, I need it to return it to me. And if it doesn't have the where clause, I need to create an empty version of the contents of the where clause. So you can see line 3 on the right side that I take the item FN input and say .sig, that gets me to a particular field, .generics gets me to a subfield, .where clause gets me to another subfield, and then do Rust pattern matching to see if that where clause is actually there. And if it is, I pull out one of its parts called predicate. And if it's not, I use the parse quote that we saw from rule 2 to create an empty, basically an empty predicate structure, which is you can see the return type line 2. It's something called a punctuated where clause comma. And again, we know that because we used the AST Explorer to find out what types were expected. So now we have at least a handle on passing in the user's thing, in my case, a function, knowing how to converting it into a syntax tree, being able to see what kind of structs and enums we expect the syntax tree to contain. We might get to a point where we want to actually generate some new code that's different from the user's old code. The simplest way to do that, and should definitely be done when it works for you, is to use the parse quote macro. And another important way that's not too hard is with Rust's update syntax. So first, the parse quote. In my macro, I need to create a line of code. It will be the first statement, and it'll become the first statement in the user's function. We saw the case where I had S was an any string, and I wanted it to say S equals S, let S equal S dot asref. So on line 1, we're passing in an identifier. In the scenario I'm talking about, it would be S, the variable input, the variable, the letter the user is using for input. And you can see lines 4, 5, and 6 is where it generates this new statement that's going to become S equals S dot asref. And you can see it's got this kind of substitution syntax with the pound sign that actually makes it pretty fun to use. In the case of iterators, we still generate a statement, but it's a little bit different. It would be like iterator 1, let iterator 1 equal iterator 1 dot into iterator. And in the case of my multidimensional arrays, it's yet another line that we would want to add. But in all the cases, it's the parse quote makes it pretty fun to generate new code, and we can put in our own, we can substitute in our own values. The other straightforward way of generating code is when you want to generate a new struct. So on the right side, I want to generate a new item function. So I say, okay, I want a new item function. The first field is sig, and then I've got some expression that tells how I want to set that field. The second field is block, and I have got some expression to say how to set that field. It's got 2 more fields. I don't want to change them. I want them to be exactly what they were before. So just standard Rust feature is that you can, when you're filling in a struct, you can say dot dot some other structure that's the same type, in this case clone, and it'll just fill in the last two fields of my new item function that it's creating with whatever values it had from old fn. It's at line 12. If you've only got 4 fields, then maybe it's not that important. I could have just specified all 4. But if we look at line, I think line 3, signature, I'm creating a new struct of type signature. I set the generics field to something that I know I want it to be. I set the inputs field to be what I want it to be. And then I say the rest of the fields should just be the same as they were before. That's line 6. And this saves me a lot of typing because I think signature has 9 fields. So this was just a nice standard Rust way of creating new structures based on old structures and not having to specify every single field explicitly. Let's go on to the next. So it would be nice if we could do all our programming destructing and constructing our structs and enums with the methods I've said so far. But it doesn't work because some of these structures get really complicated because they can be very recursive. So for example, we've seen things where our user might have said, had a function with an input s is any string. Okay, that's not that complicated. They could also say v is a vect of any path. It's like, okay, that's a little more complicated. Now our special pseudotype is inside a standard type vect. Or we could have a is an any array of any path. So now we've got 2 of our pseudotypes nested. It's getting more complicated. Even worse, say they have a variable called yikes, and it's a pseudotype special, I'll say pseudotype, any iter where each element is a vec, where each element of the vect is any array, where each element of the array is any path. And you can just look at that and see that you're going to have to use recursion to handle cases like this. So the good news is the syncrate provides a nice mechanism for doing all the recursion that we need for both visiting and creating, manipulating syntax trees recursively. It's all attached to the fold crate. The way it works is you tell it to start recursively processing some syntax tree, and then for all the types that you want to do something special with, and it knows there are 187 syntax tree structs and types. The ones you care about, you tell it to do something special for those types. The ones you don't tell it about, it'll do nothing as a default. Sometimes when you're doing the recursion, your type, in my case, something you want to manipulate, might itself be built to have subparts that are also something you want to manipulate. So you have to do recursion within recursion, nested types. It can still handle that, but you have to be careful that you set that up the right way or you'll miss the inner one. And that's too complicated to explain now, but look at the article. It's not too bad. It's just a special line that you have to put at the right place. Okay, that was all. I think that's all the programming, inner programming syntax tree stuff. So let's talk about error handling. Rule 7 is use the proc macro error crate. All Rust code needs to handle errors, of course. Sadly, macros don't use the Rust result types that we're used to in regular coding. We know that we don't use results. We can often just call panic, which isn't as good as results, but is something. That kind of works with macros, but not perfectly, because when we return an error message in a macro, we want to be able to point to the part of the user's code that caused the error. We want a location. And if we call panic, like we would in normal code, it won't have the location information. One moment. There are a couple efforts to improve this situation, but within proper formal official Rust, but they're either in nightly and they don't seem to be working their way out very quickly, or they only work as on your top level function. They aren't something that you could call when you're recursed 4 levels deep, parsing the user's code. So the good news is someone has created a third-party crate called proc macro error, and it does exactly what we want. It's just like panic, except we say abort and we can give a location. The downside to it is that it brings in some overhead and makes it slower. I think it's more than worth it because it does exactly what we want. And it's also trying to be compatible with the way that things might officially get standardized. So you'll only have to make little changes going forward if the error handling in macros story matures. So here's an example. Inside my macros code, I check to see whether the user, when I have nested pseudotypes, they should be using the angle bracket. So like any iter of any string should have an angled bracket. If the user does a round bracket, I will detect that in this function at the top, and I just call abort. Span range is something that I was able to easily bring in from the user's code to say which code caused the problem. And I just return a string. When the user actually calls the macro, they'll get this nice underline. You see at line 5 showing where the problem was, and a nice error message, expected angled bracket generic parameter. So I'm really happy that this macro, that this third-party crate exists, because it makes things very sensible. Rule 8 is do integration testing, including UI testing, specifically with try-build. Everything we did for testing so far was down at the lowest core level. We were calling our function that the macro calls, but we weren't really seeing what happens when the real compiler calls our macro before doing its compilation. To do that kind of testing, you have to do it at the topmost level, and you should do that. Here's an example. This is just a top level test. We have a test called anyinput. It has a function inside it where we define any string length, with s being of my pseudotype any string, and it just returns the length. And we just assert that the any string length of 1, 2, 3 in quotes is equal to 3. So that's a very nice integration test. The compiler is really running the macro, and everything is good there. The only problem is, along with testing that it works well, we also need to test that when the user makes a mistake, that it's giving the right error messages. And to do that, we create a test we'll call UI tests that use the try-build crate. The way the try-build crate works, and people use it for other things too, is you create little bits of Rust code in a directory, like a UI directory shown on the lower line 4. So like test1.rs, test2.rs, whatever you want. The try-build will find your files, run them through the compiler, expect them to fail, check that the standard error strings produced by the failure are what you expect. And if they are what you expect, then the test passes. And if they're different than what you expect, the test fails. The way it knows what to expect, the first time you can let it run, it won't know what to expect, but it'll output what standard error it actually saw. And if you can look at that, and if you like it, you can put it in the right directory. And then from then on, it'll check that it is consistently creating the same error messages that it should be creating. All this testing at multiple levels seems complicated, but if you set things up with the workspace mechanism I mentioned before, then you can run all your low-level unit tests and all your integration tests just by saying cargo test __ workspace. Okay, our final rule. The final rule is to follow the rules of elegant Rust API design. That had 9 more rules. The 3 most important ones, though, are to use Clippy, which is the linter that checks that you're kind of doing things nice. You got your capitalization of variables right and all that. You should make sure you write good documentation because you're designing something for other people to use. And if you can't explain how to use it, then maybe your design isn't good. And you should test your design on your own projects, what we call eating your own dog food. So I had 2 Rust crates that I tested this on, the anyinput macro in. I have one called fetch data, which downloads and caches big sample files from the internet. It's compatible with Python's popular pooch package. That was just so when a user gave me a path of something, it could be a string or a path or a reference to a path. That worked fine, but that was a very simple case. The more complicated case was bedreader, where I actually had iterators of strings and things like that. And when I first did it, I was surprised because when I looked at the documentation that bedreader generates, it turns out that for all these procedural macros, the documentation uses the version of the functions or data structures after the macro has run. So I had a function in bedreader called chromosome that passed in an iterator of any kind of string, but the documentation actually shows the generic types that the macro generates. And the first time I did this, I was using types like T0, T1, and that was hard for the user to read and might conflict with their own generic types. And then I did big, long, random types, so there wouldn't be any chance of conflict, and that became too hard to read. And so I ended up with this, where I created generic types like any string 1, any iterator, any string 0, any iterator 1, which seemed like I'm satisfied with this design. And the reason I found it is because I actually applied my macro to a real project and got to exercise it. Okay, so this is my last slide. The conclusion is, if you follow these 9 rules, you can make writing macros as easy as writing regular Rust programs. Regular Rust programs that manipulate large nested structures. So it's kind of easy, but still not super easy. The plus is that with procedural macros, you can do almost anything. If many of us love Rust. If there's anything you think could be better, you can actually make it better yourself. If there's any redundancy you see in your own code, just because of your project, you have a chance to remove that redundancy to make the language more productive for you. The minus is that some things seem hard when you're creating procedural macros, debugging, testing, error handling, understanding syntax trees. I think all those are made easier if you follow these rules, which require you just set things up right, and things do get easier and become easy under these rules. And it really does allow you to unleash your productivity. So that's the end of the presentation. Thank you.